Hello everybody, welcome to today's lecture. So today we're going to start talking about 3.2. Last time we talked about 3.1, so let's just quickly look at what we did there, because we're going to build off of that today. So we started talking about probability. So we laid out some of the preliminary definitions, like what the sample space is. That's all the possible outcomes we can have. So like if you're flipping a coin, your possible outcomes are heads or tails, right? So this is an example of a sample space right here. An event is any combination of outcomes, and we usually use capital letters to represent the events. And the way we write the probability of an event is P of A. So it's like P parentheses A. Okay. All probabilities are between 0 and 1. You can represent them as percentages, so they would be between 0% and 100%. So you want to know how to flip between decimals and percents. Normally our answers are going to be in decimals, but usually it's easier to intuitively think about it as a percentage, right? So then to find probabilities, you just count the total number of ways an event can happen and divide by the number of total possible events. So like, or total possible outcomes. So we had some examples here. And then we talked a little bit about OR events and events. We're going to talk more about them in 3.3 because to really dive into them, we need to talk about conditional probability and independent events, which is the subject of 3.2. Okay. So let's dive into conditional probabilities. So this is the end of 3.1. Okay. So the conditional probability, before I write the notation here, this is the kind of thing of like, what's the probability that A happens if we know that B happens? Okay. So it's conditioning on a different event. It's like we already know that B happens, so what's the probability that A happens now? So for example, if we flip a coin twice, what's the probability of getting heads on the second one if we got tails on the first one? Okay. In that case, there's no difference, right? Because what happened on the first flip doesn't mean anything for the second flip. But think about like if we have a standard deck of cards, right? And we have 52 cards. So what if we said, what's the probability of drawing a 4 given that on the first, so we're thinking about drawing a card twice, okay? So what's the probability of drawing a 4 on the second draw, given that we drew a 3 on the first draw? Okay. There is going to be a slight difference there because if we drew the 3, assuming we didn't put it back in, now there's only 51 cards in the deck, right? So there's going to be a difference. Maybe it's more clear to see a difference if I say, what's the probability of drawing a 4 on the second draw, given that we drew a 4 on the first draw, right? There's 4 4s in the deck. There's 4 of any card in the deck. We already drew one of them in the first one. So assuming we didn't put it back, the probability is going to be, so the probability on the first one is just 4 out of 52 because there's 4 4s in the deck, 52 cards. But now on the second draw, it's going to be 3 out of 51 because there's 3 cards left and only 51 cards left. So it's going to be different. So the way we express this is with conditional probabilities. So the conditional probability of A given B, so this means the probability that A happens given that B already happened, is written like this, okay? So it's like our probability that we wrote up there with the parentheses, but now on the inside we have A and then a bar and then B. Okay, so it's just a straight bar, and we read this as the probability of A given B. Okay, meaning what's the probability that A happens given that B already happened? So this bar means given. Um, so let me look here. So what's the formula for this? Okay. So the probability of A given B, well, we have to think about what happens here, right? The probability of A given B, first of all, we're looking for what's the chance of A happening, and we're assuming B already happened. Okay. So, but B still has to have happened, right? So in the formula, we have the probability of A and B happening. Okay. So the probability of A given B is equal to the probability of A and B, but because we're assuming B already happened, we also want to divide out the probability of B. Okay. So hopefully that's a decent explanation for where this formula comes from. It's hard to really put into words like intuitively why this happens. It will make a little bit more sense after the next chapter when we talk about independent events, because we'll see that with the way this is set up, if A and B are independent, meaning they don't influence each other, this formula simplifies to just probability of A. The probability of B parts cancel out. So it's kind of like we're taking the probability that both A and B happen, but we're getting rid of the probability of B part because we're assuming that happens. We're assuming that that B did happen. So we don't really need to think about the probability of it happening. So we take the probability of A and B happening and divide out the probability of B part because we already have that. We already know that's true. Okay. Okay. Maybe an easier way to think about this would be if we rearrange it. So if we times both sides by the probability of B. Okay, so this is equivalent. This is how we write equivalent. Let me write this better. So it's like an equal sign with two arrows on each side. Hard to write neatly. So if we multiply both sides by probability of B, we have probability of A and B equals probability of A given B times the probability of B. Okay, this one might be easier to think about because, okay, what's the probability of A and B happening? Well, it's going to be the probability of B happening times the probability of A happening given that B happened. Okay. So we need two things. We need B to happen and we need A to happen, right? So this is this is exactly what's written here. So we have the probability of B. It's not just the probability of A because we also have to think about the fact that B already happened, right? And so that's what we have here. If A and B have nothing to do with each other, again, this will just simplify to the probability of A times the probability of B, which we'll talk about in 3.3. Alternatively, it could just be the other direction too. Probability of A, B given A times the probability of A. Okay. These would be equivalent. because the probability of A and B, it could be the same thing. It could be the probability of A, and then you just need A and B to happen, so you could do it in the opposite direction. You have probability of A, and then the probability of B given that A already happened. Okay, so it doesn't matter which one you make conditional. It still leads to the same formula. But anyway, this is the formula that we want to use. Okay. And these two are just rearrangements of it. All right, let's talk about, oh, and I should also specify, because we have division here, probability of B cannot be 0. If the probability of B is 0, this statement doesn't make any sense. Probability of A given B, because this is a probability of A given that B happened, but if the probability of B happening is 0, then we can't possibly talk about B happening, right? So that's the intuitive explanation. The math explanation is that we can't divide by 0, right? So let's think about the book has an example, but I think we can make a better one. Let's think about a deck of cards like I was talking about. Okay. So let's let A be the event that we draw a, let's say, queen. And B be the event that we draw a 7. Okay. So what's the probability of A given B? And we're assuming like these are different draws, right? So what's the probability that we draw a queen given that we already drew a 7? And we're assuming we're not putting it back in the deck, okay? That's something called without replacement that we'll talk about in the next chapter. But we're not putting this. So what's the probability of drawing a queen given that we already drew a 7 and we didn't put it back in the deck? Okay. So I already talked about this verbally, but let's, so if we just think about it, well, if we drew a queen the first time, there's 52 cards in a deck, right? Let's establish that first. There's 4 of each number. Queen would be like a number, right? And there's 4 of each suit also, but we're not even talking about suits, so that doesn't matter. So we drew a queen the first time. So that means that because we took that out, there's 51 cards left. And there's still 4 7s left, right? We didn't touch the 7s. So the probability, or I think I said it backwards. We already drew a 7. Yeah. We already drew a 7. So we took the 7 out. So now there's 4 queens left, but there's 1 less card, right? So it's 4 out of 51, if we just think about it that way. Okay. So that's how we would do it this way, but how do we do it in terms of the formula? Okay. So thinking it through is one thing. How do we reconcile this with the formula now? So this is the probability of A and B divided by the probability of B. Okay. The bottom part's the easy part. What's the probability of drawing a 7? Well, there's 4 7s, there's 52 cards. So on the bottom, we have 4 out of 52, right? So what is the probability of A and B happening? That's what we need to think about now. So what's the probability that we draw a queen and that we draw a 7? Okay. So this is a little tricky. The way we were doing this before is we were writing out the sample space A and B, right? So remember, B is the first draw, A is the second draw. So what's the probability of both getting a 7 the first time and getting a queen the second time? Okay. So, here, I'm trying to think of how to do this without using the later formulas. Let me think about this for 1 second. Okay, I don't think there's any simple way to do this without using the formulas in the next chapter. The main idea is that if you have like sequential events, like what's probably of this happening and then this happening, like basically the way to figure out probability of A and B is to use this formula, which isn't really helpful here because we already, like, this is what we're trying to find, and we can find that just by reasoning through it. But if we did that, then we come up with 4 out of 52 times 4 out of 51, because that's what this formula would be, right? Probability of B is 4 out of 52. Probability of A given B is 4 out of 51, like we already found. And then they cancel out, and then you get 4 out of 51. But it's not really helpful. It's very circular reasoning. So maybe this wasn't the best example for this. I think it'll be better to look at some more examples of this after we talk about the next section instead. So let's just move on to the next section, and then we'll see more examples come up after that. Okay. All right, so I apologize for struggling through this example here. There is a decent one in the book if you want to look through that. But we'll just move on to the next one. Because usually, so the reason I'm not really worried about it is because usually when we're doing these kind of problems, it's going to be in the context we're going to talk about, which is independent events. So let's look at this chapter then. This chapter is called Independent and Mutually Exclusive Events. Okay. So independent is what we're going to talk about first. So the meaning of independent is that the events, they don't have anything to do with each other, right? So the outcome of one does not affect the outcome of the other one. So like if you flip a coin twice, whatever you get on the first flip is not affecting what you get on the second flip, right? If you get heads on the first one, it's not going to make it more or less likely that you get heads or tails on the second one, right? So in math, two events, A and B, get rid of that, are independent if the following are true. Okay. So the first would be that probability of A given B is equal to the probability of A. Okay. So this means that the probability that A given that B happened is the same thing as just the probability of A, meaning that B is not influencing A at all. Okay. Also, the opposite should be true. The probability of B given A is just the probability of B. So B is not influencing A, nor is A influencing B. So the probability of B happening is the same whether or not A happened. Okay. So we don't need to consider A at all when we're thinking about B. So on that second coin flip, we don't need to consider what happened on the first coin flip. We still have a 50-50 chance of getting heads or tails. Okay. In our deck of cards, with this one, I was talking about not putting the card back in. But if we did put the card back in, then what happens on that second draw is independent of what happened on the first draw, because we put the card back in and now it's the same deck of cards, right? Lastly, the most important one that we are going to use is the probability of A and B is equal to the probability of A times the probability of B. Okay. So we get to multiply them together. If two events are independent, then the probability that they both happened is just equal to the product of the probability that each one happened. So this is a really useful formula. If we go back to our formula from the last one, the probability of A given B equals the probability of A and B divided by the probability of B. If we assume A and B are independent, so I'll just abbreviate it as IND. Well, given by number 3, probability of A and B is probability of A times probability of B. Okay, so now the probability of B's cancel out, and we just have probability of A. So we have probability of A given B equals probability of A, which is number 1, right? So you really just need one of these, and then you can derive the other two. But yeah, these are all consequences of A and B being independent. So in words, two events A and B are independent if the knowledge that one occurred does not affect the chance that the other occurs. Okay. So, like I said, knowing that one happened or the fact that one happened isn't influencing another one happening. So that second coin flip isn't influenced by what happened on the first coin flip, right? So, this leads to a common fallacy, which is a like illogical reasoning. In critical thinking, we call it fallacies. It leads to a common fallacy called the gambler's fallacy. which is confusing independent events for non-independent events. So, for example, if we flip a coin 10 times and on the first 9 we get heads, then oftentimes people will be inclined to use that information to guess what the 10th coin flip is going to be. Maybe they say it's going to be heads because it's all been heads. Or maybe they think it's going to be tails because they think that they're due for a tails, right? And neither of those are sound reasoning, because what happens on that 10th coin flip is independent of what happened on the first 9, right? The first 9 don't have any influence on the 10, even though it seems like there's a pattern. It's just random chance. So the gambler's fallacy is making a bet on the next outcome, even though based on the previous outcome, even though they're independent. Okay. So if you study critical thinking, that's something that might come up. This concept is going to be very important to us in statistics, because a lot of times the statistical tools that we use are only going to apply if our data is independent, or at least it's going to be a lot easier if our data is independent. So this is very important. The opposite, by the way, of independent would be dependent. Okay. So our data does depend on the other one. So if we're drawing cards without putting them back in, what we get on this, the probability of the second card is going to depend on what you got in the first card. Right. So let's talk about with replacement. Versus without replacement. Okay. So if we do an experiment with replacement, that means, like in the drawing card example, that means that after we draw the card in the first one, we put it back into the deck. Okay, and then we shuffle. In the second, in the without replacement, if we're selecting without replacement, that means when we draw the card out, we don't replace it. We just leave it out. Okay. So this will be seen in any example where we're like drawing something. Like maybe you have a bunch of marbles in a bag. That's a common example. Say there's like 10 red marbles, 10 blue marbles, 5 green marbles. And you're looking at the probability of like drawing a red marble. So this kind of sampling can either be done with replacement or without replacement. So you either take the marble out and then you put it back in after you see what it is, or you take the marble out and you leave it out. Okay. So this could be done when we're randomly sampling for a population in statistics too. If you're sending out surveys randomly to people, like say you send out a survey and then you wait for somebody to fill it out before you send out the next one, is it still possible that you send one to that same person, right? Couldn't they get a second survey, or are they taken out of the population, or are they taken out of like your mailing list or whatever, and then you send it randomly to another person? Okay. So I won't write down the definitions of these exactly, because I think the wording of them kind of is the definition, right? You either replace it or you don't replace it. The book has kind of a more long-winded explanation, or a more long-winded definition, if you would like a different definition of this. Okay. So in general, if the problem doesn't tell us whether or not two things are independent, then we just have to assume that they're not, right? And hopefully the math will kind of show us along the way. But if it's not told to us, we just have to assume that they're not and work with that. And maybe it'll turn out that they are, and then the math will be easier. Usually things are easier if they are independent. But if it's not told to us, we can't make that assumption. Okay. So, and in general, like when we're doing things with replacement, that's going to make the events independent. Whereas if it's without replacement, then they won't be independent, right? Okay. So let's talk about, so we said independent and mutually exclusive. These are two things that seem pretty similar and are often used interchangeably when they really shouldn't be. Okay. So independent is when two events don't influence each other. Mutually exclusive events are a little bit different. Okay. So A and B are mutually exclusive events if they cannot occur at the same time. Okay. In other words, probability of A and B is equal to 0. Right. Another easy example of this would be like a coin flip, right? If A is heads and B is tails, or we could just write it out even. The probability of heads and tails, if we flip a coin one time, is of course going to be 0 because we can't get heads and tails at the same time, right? It's either going to be heads or it's going to be tails. It can't land on both of them. If we think about it like a Venn diagram, okay, this is A, this is B, and there's no overlap between them, right? So these are mutually exclusive. If they're not mutually exclusive, then they would have like a shared region, right? This is A, this is B, this is A and B. So these are independent, or these are mutually exclusive. These are not mutually exclusive. Okay. Just like with independence, if we're not told whether or not they're mutually exclusive, we just have to assume that they're not. Okay. So this is talked about more in 3.3, but independent events relates to the probability of A and B happening. Here, with mutually exclusive events, probability of A and B happening is 0. So this actually allows us to talk about the probability of A or B happening a little easier. Okay, the probability of A or B. What did we say about these in 3.1? Not much. We just wrote a new sample space, right? Let's think about how this, if A and B are mutually exclusive, how would that change probability of A or B? And this Venn diagram will help. Well, the probability of A or B happening, if they're mutually exclusive, it's just going to be the probability that A happens plus the probability of B happening. Okay. because they're completely separated. So the probability that either one of them happens is just going to be the probability that we get in this region or the probability that we get in this region. Because there's no overlap, we can just add them together. If there is overlap, then when we add them together, then notice that if we have probability of A and the probability of B, we've counted that middle region twice, right? So if they're not mutually exclusive, what we have to do is because we count that middle region twice, then what we have to do is subtract one of them off, because otherwise we're overcounting. So we add them together, but because now we counted the middle region twice, we have to subtract one of them off. Let me move this. Okay. So when they're not mutually exclusive, we have probability of A plus probability of B minus the probability that A and B happens, because we have to subtract out one of the middle regions. Now notice if they are mutually exclusive, the probability of A and B is 0. So now the equation just simplifies to this one. Okay. So you could just remember this equation and then remember that mutually exclusive means probability of A and B is 0. And now you just have this equation. Okay. So this is actually presented in 3.3. So I'm getting a little ahead of myself here. We've really already done 3.3 in this chapter. 3.3 is just what they call the addition rule, which is this rule right here, and the multiplication rule, which is this rule. If A and B are independent, then probability of A times B, A and B is probability of A times the probability of B. Okay. So I feel like we can just basically combine these chapters together, and then we'll do some examples now. So let's write. Okay, we'll delete this. So let's look at how some examples are affected. So question 1. What is the probability of getting heads 5 times in a row? So when tossing a coin, of course. And how do these rules help us with this? Well, let's give some notation first. Let's let HI be the event we get heads on the ith toss. Okay. So H1 will be that we get heads on the first toss. H2 will be that we get heads on the second toss. And H5 would be that we get heads on the fifth toss. Then notice H1, H2, H3, H4, and H5 are independent, right? Because every toss is a new toss. It doesn't matter what we got on the last one. So getting heads on the second toss it doesn't matter what we got on the first toss. Getting heads on the fifth toss, it doesn't matter what we got on any of the first four. Okay. So what we're looking for is the probability of H1 and H2 and H3 and H4 and H5, right? Probability that we got him on all of these. But because we know they're independent, then by this rule up here, number 3, we know we can just multiply them all together. We only did it with one and here, but when we have multiple ands, same thing. We can just multiply all of them together. Okay. So now we know the probability of getting heads is 1/2. So this is 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Okay. And so this is 1/32. So the probability of getting heads 5 times in a row is 1 in 32. So this is how we can use the and rule and the fact that they're independent. Let's look at example 3.17. So this says a student goes to the library. Let events B be the student checks out a book. And D be that the student checks out a DVD. Okay. Suppose the probability of B equals 0.4, 0.40. Probability of D equals 0.30. So probability of checking out a book is 40%. Probability of checking out a DVD is 30%. And the probability of D given B is 0.5. Okay. So first question, find probability of B and D. All right, so a student goes to the library. The probability of them checking out a book is 40%. The probability of them checking out a DVD is 30%. Now, the probability that they check out a DVD, given that they already checked out a book, is 50%. So this tells us something really important, and that's that B and D are not independent. If they were independent, then the probability of D and the probability of D given B would be the same thing, right? But they're not. Now, let me put a 0 after that just to be consistent. So this and this are not the same thing. That means they can't be independent. So this is not just the probability of B times the probability of D. We can't break it up like that because they're not independent. But we have another formula. Going back up here, actually, sorry, going back to the last section at the bottom here, we can use the rearrangement here, right? The probability of A and B is the probability of A given B times probability of B, this whole thing. So this is the probability of D given B times the probability of D. Wait. No, the probability of B. Yeah, we want to make sure we have them in the right order. If D is first here and B is second, this should be the second one. See, probability of A given B times probability of B. So it should be the second one. So, and then these numbers are given to us, so all we have to do is plug them in. This is 0.5 times 0.4, right? And then you can just do that in your calculator, 0.5 times 0.4, and you get 0.2. Okay. So the probability of them checking out both a book and a DVD is 20%. Okay. So we need the fact that they check out a book, and then the fact that they check out a DVD given that they check out a book. And then we just end up multiplying those together. So 0.4 times 0.5. Okay. So just using the formulas here. B is the other question. Find the probability of B or D. Okay. So this is going back to this formula, A or B, right? So what we have to determine is, are B and D mutually exclusive? That would mean that that the probability B and D is 0, which given part A, it's not true, right? So this is going to be using the second formula here. They're not mutually exclusive, so it's going to be the probability of one plus the other one minus both of them happening. So this is going to be the probability of B plus the probability of D minus the probability that they both happen. And then we can just plug in our numbers because we already found that last part in part 1. So this is going to be 0.4 plus 0.3 minus 0.2. Okay. So we get 0.5. So the probability that they check out either a book or a DVD is 50%. Okay. This one, I think it tricks our intuition a little bit because we see the book and the DVD and we think, okay, what's the probability that you check out either one of them? I think our brains, at least my brain, wants to just add them together. But we're forgetting the fact that there could be some people who check out both, so there could be some overlap in these, right? So they're not mutually exclusive events. We're forgetting about that overlap if we do that. So that's why we have to minus that overlap. And then we found the overlap in part 1. Okay. All right, so there's lots of different examples like this. You can let me know if we want to do more of them, and I can do them at the beginning of the next lecture. There will be a lot of them on the homework like this because it's very important to do these on your own. This can be very tricky. It was very tricky for me when I started this. I felt like it was betraying my intuition a lot. And so I really just had to, like, at times, kind of forget about the intuition I had and trust the math. And eventually, after enough practice, it became my intuition. And I just kind of got used to it. And my intuition and the math agreed. But at the beginning, I remember they didn't. My intuition was very different from what the math was telling me. So it's important to do a lot of examples so that we kind of gain an intuition for this. Because it's typically different from something we've seen before. So, um, that can make it tricky at first. So just make sure you do some examples here and let me know if you want to see more of them. The book has a lot of them, so that's a good place to get some more if you'd like to see them as well. So next time we'll go on with chapter 3. There's really not a whole lot in this chapter. So we won't be spending too much time on this chapter, and then we'll go on to 4 and 5, which also have to do with probability. And then after that, we'll kind of see how this relates back to statistics now, because we're kind of taking a sidestep into probability, but we need to get back to statistics. So we'll see how it relates to that. So thanks for watching this lecture, and I will see you guys on the next one.